On the night of September the 29th, 1959, Braniff flight number 542 took off from Houston, Texas, on its way to New York International Airport. The plane was a Lockheed Electra L-188, a brand new aircraft, just 10 days old. The night was humid and the weather clear, as the passengers settled back for a long journey. After reporting to flight control in Dallas, Second Officer Roland Longhill wrote in his logbook the words, "Transmission complete." It was the last communication from Flight 542. The story of the Lockheed Electra is a story about detective work, the painstaking piecing together of evidence in an attempt to understand a fatal flaw in the design of a plane. This is also the story of mathematics and its role in aerodynamic surface design. Holt Ashley is the author of a number of books on the mathematics of aeroplane design.
It was developed as a, at that time, long-range jet transport by the Lockheed Aircraft Company in Southern California. Four-engine, straight wing, but using early turboprop technology.
34 people died when Flight 542 went down over Buffalo, Texas, on a calm, still evening. What was needed was an explanation of why it had happened.
There were two factors which had to come together in order to lead to this unfortunate accident. First of all, one or more of the attachment points, the supports of the engine to the wing, had to have failed in some way, weakened or broken. And secondly, there had to be an encounter with an atmospheric gust or with turbulence, something which caused a bump to occur in the wing and the engine and everything.
Investigators of the Buffalo crash knew that one of the aeroplane's wings had become separated from the plane. What they didn't know was why. The Lockheed Company, along with the Federal Aviation Authority, set a group of engineers the task of piecing together the events of that night. When the investigation began, there was little to suggest that the problem was one that is fundamental to engineering design. 20 years earlier had seen the completion of the Tacoma Narrows Bridge in Washington State. Spanning over a mile, it was the culmination of many years of bridge design and a monument to the future with all that new technology had to offer. Unfortunately, the bridge was fatally flawed. The design had not taken into account some fundamental aspects of the mathematics of aerodynamic design, with disastrous effects. Many years after the Tacoma incident, public interest was again focused on the collapse of a large architectural structure. The Ferrybridge power station in the north of England was just one of the generation of coal-burning facilities. The 8 large cooling towers dominated the landscape until the evening of the 1st of November, 1965. Like the Tacoma Bridge, the Ferrybridge disaster took place during high winds. But these towers did not simply blow down. The Ferrybridge cooling towers were designed, like many others, to be a particular shape. Known as the hyperboloid of one sheet, this shape has some unique mathematical properties that make it extremely strong. It's a member of the family of shapes known as the non-degenerate quadrics, three-dimensional versions of the conics, which also includes the ellipsoid, the hyperboloid of two sheets, the elliptic cone, elliptic paraboloid, and finally, the hyperbolic paraboloid. Each of these surfaces is strong, but the hyperboloid of one sheet and hyperbolic paraboloid share two features that make them particularly suitable for building, and unlikely that the cooling towers simply fell down. During the late 50s, many architects began to use hyperbolic paraboloid in roof design. One architect practicing at that time used the shape on 3 of his buildings.
The hyperbolic paraboloid has an exciting form which is very flexible, and one gets a little bit tired, or one got a little bit tired, of the horizontal and the vertical. It was also structurally very effective and economical. And I think these two interests are why I and many other architects got interested in the hyperbolic paraboloid.
The first of Sam's buildings stands on the edge of Brayford Pool in Lincoln. Now a library, that was not its original purpose.
The building, which is now a library, was originally designed as a garage. They wanted a large open space in which cars could be moved around and serviced over some pits. And the site allowed this space to be about 110 feet by 100 feet. And the problem was therefore, how do you put a roof over this space? The building owner didn't want just a utilitarian building. He thought he would like to have something which was interesting architecturally. We eventually made a system of 4 shells, but split them down the middle into 2 lots of 2 with a roof light, so that you get natural daylight.
For architects interested in the hyperbolic paraboloid, one of the attractions of the shape is the large surface area that can be achieved, with a minimum amount of support. It was this that led Sam to his next project. This unusual-looking building is the Church of St. John on the Ermine Estate in Lincoln.
They wanted a building which was specifically designed as a church, and they had strong views about where the important elements of the church should be placed.
Despite the curving of the roof, the hyperbolic paraboloid is straightforward to construct, and is actually based on a family of straight lines which trace out the shape of the curve. By placing timber or steel supports along these lines, it is possible to build up the whole curved surface. Adding short wooden boards known as shuttering at right angles fills in the smooth body of the curve and completes the roof, which is then covered with a thin layer of concrete. The hyperbolic paraboloid is a saddle-shaped surface, a deformation of a flat plane. Cross-sections in 2 perpendicular directions give parabolas, and in the 3rd perpendicular direction give hyperbolas. It is still possible to see the lines of the original timber generators inside the Church of St. John the Baptist, an interesting reminder of the church's construction. But the hyperbolic paraboloid is not the only quadric that has 2 families of these straight-line generators. The hyperboloid of one sheet shares this property and is just as easy to construct. If we take 2 parallel discs and join points on the upper disc to points on the lower disc, rotating one way will give the right-handed curve, and the other gives the left-handed curve. both families of generators come together to give the hyperboloid of one sheet. Sam's most impressive project was another shell roof. But this time, he used just one hyperbolic paraboloid.
The third shell which we built was as a result of an inquiry from somebody who had seen the garage at the Brayford, which is now the library. And he thought this was an interesting shape, and he said, I want one like that. So I said, well, you don't actually want one like that. You want something with those ideas.
Now a roadside restaurant, the roof was built to cover a petrol station, and as such it needed to be able to withstand strong winds from all directions, with only a minimum number of supports, which allows space for cars to maneuver. This is the real beauty of the hyperbolic paraboloid. The doubly curved surface, being hyperbolic in one cross-section and parabolic in the other two, makes this shape extremely sturdy, while remaining attractive from any angle.
It is in tension and in compression. So you put some reinforcement in to deal with the tension, and the concrete deals with the compression, and you therefore have a very thin membrane. It's got the strength like a chicken's egg. The shells that we are using are 2.5 inches thick, spanning over 40 or 50 feet. Clearly, something as thin as that would just collapse if it hadn't got the structural shape of a hyperbolic paraboloid. It will always be an interesting shape, an interesting form, and I think it's rather a shame that the development which took place in the 50s and 60s hasn't continued positively.
The strength and integrity of the hyperbolic paraboloid has made it useful for the building of shell roofs, many of which have stood the test of time. So if the hyperboloid of one sheet shares the structural benefits of this other quadric, why did the Ferrybridge cooling towers fall down? The answer to this question and the Tacoma Bridge problem provides us with a clue to the Electra crash. It depends on linear algebra, in particular eigenvectors and eigenvalues. The Tacoma Bridge had always had a vibrational element to its behavior, even earning itself the nickname Galloping Gertie. In fact, all structures and surfaces vibrate, behaving rather like a mass on a spring. As the mass is displaced from its equilibrium position, it begins to vibrate from side to side. In most situations, the vibrations die down naturally and the mass returns to the rest position. The system is said to be damped. This is just what happens when you tap a glass and it rings. This note is the natural frequency of the glass, caused by the vibration of the glass surface. The sound quickly dies away. However, rubbing the rim of a glass results in the build-up of the vibrations, and the glass begins to ring at one particular frequency. This is known as resonance. Resonance is the rapid and uncontrolled increase in the size of a vibration when the force applied is at that natural frequency. The strong winds that blew on the night of the 7th of November 1940 had a frequency equivalent to another more destructive natural frequency of the Tacoma Bridge, and the resulting resonance was the cause of the destruction. When the gale force winds of the 1st of November 1965 were trapped by the curved sides of the Ferrybridge cooling towers, the resulting frequency was a resonant frequency of those structures. The towers began to vibrate, ringing rather like a glass, and down they fell. Six months after the fatal Braniff flight, the crash investigators were still baffled by the accident. There had been no known damage to the brand new plane, and it had not encountered turbulence or strong winds. Then on the night of the 17th of March, 1960, another Electra went down. Again, it had lost a wing, but this time there had been turbulence. This gave the investigators the clue they needed. It was possible that vibrations could have had a part to play in the loss of the Electra. All aeroplanes have surfaces and can vibrate. To analyze these vibrations, aircraft design teams use eigenvectors and eigenvalues.
The concept of eigenvalue is ordinarily used to describe something like the frequency or the period at which anything oscillates. As a simple example of an eigenvalue and an eigenvector, if you imagine just a mass attached to a base with a spring, you can put this into motion and it will oscillate.
As the number of surfaces involved begins to increase, the vibrations begin to interact. The eigenfunction equation can take many forms, but is most recognizable to the aircraft designers in this complex form. It's these elements that describe the vibrational behavior of the surface. The amplitude or size of vibration is described by this term, whereas these parts describe the frequency at which the surface vibrates. This equation only describes one of the surfaces that can vibrate. There may be thousands of similar equations that all interact.
A complicated structure, like an airplane wing, like the Electra, has not just one of these frequencies, but many. And associated with each of those frequencies is a different way in which it could vibrate. For example, the wing might bend in a relatively low frequency eigenmotion, and the eigenvector is a mathematical description of the way in which it deforms, whereas the eigenvalue is the frequency, as I was telling you. Then there might be another higher frequency one in which mostly it was twisting rather than bending. And the propeller, engine, shaft combination come together to make these even more complicated in the case of the Electra.
The Electra was a turboprop plane. The propellers were mounted on the end of long shafts connected through a gearbox. This, in turn, connected to the turbines in the engine, which spun at a much greater speed. All of the elements were then sealed within the nacelle, the outer cover of the engine. Each of these surfaces can be modeled by the spring and mass, and their interaction is very complex. By using the eigenvectors and eigenvalues as large-scale matrices, it is possible to model the behavior of different parts of the plane, and to predict and cope with the onset of resonant behavior, known as aeroelasticity or flutter.
Flutter can occur in any of the so-called lifting surfaces, like the wing, the fin, or the stabilizer, horizontal stabilizer. And it occurs when a certain speed of flight is exceeded, such that when, say, the wing is set into vibration, the air blowing by is capable of putting energy into this vibration and causing it to increase in amplitude.
The NASA Langley Research Facility had been set up to analyze flutter problems, using mathematical techniques including eigenvector and eigenvalue solutions. Lockheed crash engineers joined forces with NASA to look at the likelihood that flutter had been involved. Bob Donham was one of the Lockheed investigators.
My first assignment was to start to develop the necessary tools to study the potential of such a failure. It turned out that a very large system of mathematics had been developed, which we have, using an acronym FAMOUS, it means Flutter and Matrix Algebra System, was available to us. Flutter is basically the extraction of energy from the airstream to produce an unstable motion, usually between 2 degrees of freedom. People seeing such motion of a flag in a breeze will say it's fluttering in the breeze. This is somewhat of a misnomer, but it is true that the aerodynamics operating on the flag are the energy source that produce the motion.
flutter analysis is carried out on all planes before they are certified safe to fly. The plane is designed to absorb and control flutter through damping, so that the vibrations die away naturally. The Electra had been shown to have excellent flutter damping characteristics at and even above normal operating speeds. However, with such a complex system, it is possible to miss something. One of the eigenvalues associated with aeroplane vibrations is known as whirl flutter, or propeller autoprecession. A propeller has gyroscopic tendencies. It will whirl smoothly in one plane, not unlike a child's windmill. But if the stem becomes loose or free, then the propeller will begin to displace, the spinning of the blades acting as an energy source for the displacement. Whirl mode flutter may not have been considered in the Electra.
The major factor was to discover a process by which the propeller support stiffness was reduced. The investigators of the aircraft felt that the mating of the inlet guide vane area, where the drive shaft was going forward to the gearbox, showed evidence of this smearing effect, of such a marring effect between these motions. So that led us to the conclusion that the prop stiffness and pitch had been substantially reduced because of a failure mechanism in that circuit. So that process was the major finding of the investigators on one outboard engine on one aircraft and on the opposite side on outboard engine on the other aircraft.
A demonstration propeller model illustrates propeller whirl instability. A stiff suspension system is stable. A weak suspension system is unstable. A weak suspension system, coupled with the propeller gyroscopic motions and the aerodynamic forces, causes propeller whirl flutter.
The whirl flutter of the propeller would not alone have caused the wing to fail, unless other factors were involved. As the propeller vibrated and the engine wobbled, the frequency of vibration dropped to 3 cycles per second. Unfortunately, that was the resonant frequency of the wing. The resulting resonance snapped off the wing and the plane fell from the sky.
As a result of the combination of these factors, there built up an instability, as we call it, which was like the precession of a gyroscope. And in the process, this vibration built up in its amplitude until it caused failures, structures to break in the wing, and the entire wing was broken off.
After the loss of 97 lives and 6 months' hard work, the mystery of the Electra was solved. Now all that remained was to put it right.
Well, once we had detected the possibility of an instability, we elected to preclude that possibility by making a redundant engine mount support. We basically trapped the gearbox with mounts top, bottom, right, and left side, and added an additional mount to the engine section laterally, so that no single failure could ever free the prop plane again to a reduced stiffness level. We built a full span model of an aircraft, which we tested in the Langley tunnels at NASA, and simulated those failures and assured ourselves that these support systems would adequately prevent any possible future failure.
Putting the Electra right was reportedly a costly business, but the improvement in the stiffness mounts proved successful.
There was a repair and remodeling done with the existing Electras, the Lockheed 188A model, also called the Electra 1, and of course all the further ones which were built and sold were repaired and improved. It's clear that the repair was successful because there's been no more accidents of this kind.
The Electra soon gave way to the faster and bigger jet planes, and most were taken out of service. But that was not the end of the story. It was later remodeled as the Lockheed P-3 Orion, one of the most popular long-range naval reconnaissance planes ever built.
The airplane is used in many countries. It's still operational in service use, mostly as freighters, but they are still in service around the world.
Used by governments worldwide, the P-3 Orion is almost identical in design to the Electra, and its continued use demonstrates the high regard in which the plane is held. Mathematical analysis as complex as the solution of eigenvalues and eigenvectors has been made easier by the introduction of digital computers. Hopefully, problems like those experienced by the Electra should now be a thing of the past. But mathematics is still very much a part of engineering design and the realization of large-scale projects. Just as the problems with the Tacoma Narrows Bridge and the Ferry Bridge cooling towers help to illustrate the sometimes destructive nature of resonant vibrations, the story of the Electra helps to bring home the importance of sound mathematical evaluation. It was unfortunate for all concerned that no turbulence was ever recorded in the area of the first disaster. If the flutter issue had been mooted at that stage, the subsequent disaster may never have happened. What seems likely is that upon experiencing some whirl-mode flutter, the pilot pulled the plane up sharp, a standard maneuver in the circumstances. This was likely to have been the trigger needed to cause the resonant reaction in the wing, and the loss of Flight 542.